Welcome to the course on molecules in motion. In the last class, we were talking about the transport properties of a perfect gas or ideal gas. What we had discussed were the various transport properties and how are they going, empirical equations, summary of empirical equations, which we see whatever observations we make in our daily lives, we do experiments and summarize them, empirically summarize them and model them to get a equation. These are based on experimental studies. We had talked about how the transport occurs when you have a gradient in material or matter. We get a flux generated. Flux is nothing but the number of whatever property passing through a window with a certain area at unit time divided by that area of the window divided by time. This is known as the flux of that property is going to be proportional to a gradient of that another related property. And we had talked about matter, transport of matter or mass or flux of matter, and we had talked about giving rise to diffusion. We had also talked about transfer of energy, transport of energy, that is flux of energy, which was proportional to the gradient in temperature, and these two we had discussed. Today we are going to continue with that same the transport property of perfect gases and discuss another phenomenological equation which is related to viscosity. First, let me discuss what it is, then I will go into the final part. Viscosity, if you see, if you have these are parallel plates which you have. Okay. Suppose this plate is moved along the z axis, okay, and you have a fluid flowing through it. I am not saying liquid, I am saying a fluid, it is gas. So, if you are having a fluid flowing through it, what happens? The viscosity is what is, you all know what is viscosity. Viscosity is the measure of the resistance that a fluid offers to a applied shearing force. Okay, this is the shearing force, which is a velocity gradient in the fluid in a fluid due to a shearing action, because if you have something moving here and there is a gradient along here, then you have a shear which is generated. So, what you have a viscosity as a measure of resistance that a fluid offers, the fluid offers to an applied shearing force. And so, you are applying a shear force, and whatever resistance you have which is generated by the fluid is the measure of the viscosity of that fluid. Now, consider what is happening. Consider what happens to a fluid between parallel plates. Okay, two parallel plates or planes. This is one, this is one. When the top plane is moved along x axis at a constant relative speed with respect to the bottom, while maintaining a constant distance in the z coordinate. This is the z. So, what we are doing? We are having parallel planes. These are two parallel planes. What we are doing? A fluid, consider what happens to the fluid which is in between two parallel plates, and the top plane is moved along x axis at a constant relative speed with respect to the bottom layer, bottom of the plate, while maintaining a constant distance between the two planes. This does not change, this remains the same. So, the layer of the fluid immediately adjacent to the moving, this is the layer which is moving, this is the plane which is moving. The layer which is immediately adjacent to this moving plane will move with the velocity of the plane which is moving. the layer next to the stationary, suppose this is stationary. So, the layer next to the stationary will always remain stationary, and in between the planes, the velocity usually changes linearly with distance along the z axis. So, just visualize what we are talking about. We are talking about two planes, one is stationary and another is moved with a relative speed with respect to the one which is in the bottom. This is going, some fluid is there which is flowing within the two plates. Now, what will happen? The layer which is in the closest with the plane which is moving, this is moving with a relative speed with respect to the bottom plane. So, the speed with which this velocity with which this plane is moving, the layer adjacent, what fluid layer which is adjacent to the layer plane will have the same velocity as the velocity of the moving plane along x direction, and the one which is adjacent to the stationary plane, that fluid plane, that plane of fluid will remain stationary. Okay. So, in between the two planes, which is supposed to be a constant distance, always maintain a constant, velocity usually changes with the linear direction along the z. See, here it was almost stationary, and this was the velocity of the moving plane. So, in between, the gradient of velocity is expected as there is a linear distance along the z. Okay. So, let us consider the velocity gradient. The velocity gradient, that is what do we call the gradient as? The rate of change of velocity with respect to distance. How is it measured? Is measured perpendicular to the direction of the flow. Okay. The velocity gradient, just have a look, how do we measure the velocity gradient? Velocity gradient, that is the rate of change of velocity with respect to distance, is measured perpendicular to the direction of the flow. Which is the direction of the flow? This is the direction of the flow. So, the velocity gradient is supposed to be should be measured perpendicular to that along this. So, the velocity gradient which we are going to see, if velocity is along the movement is along the x direction, then the velocity gradient should be the change in velocity with respect to the distance dx dz, because this is the perpendicular distance perpendicular to the direction to which the fluid is flowing. Okay. So, and this is represented by, as you see, dvx by dz. dz is the distance direction in which is perpendicular to the direction of the flow of the fluid. This is along the velocity. This velocity x is representing the movement of the fluid along the x axis, and this is the z axis which is perpendicular to the flow of the direction of the flow of the fluid. Okay. Now, the viscosity eta is defined in the form of this equation. F is the force per unit area. This force per unit area is proportional to the velocity gradient. Okay. And this F is the force per unit area required to move one plane relative to the other, like one is the plane one here and the other one is here. Okay. This force is the force per unit area required to move one plane relative to the other. Means, if I am talking about this movement of this with respect to this. Okay. The negative sign comes from the fact that the F, the force per unit area, is in the positive x direction. That means, the force which you are required to move the plane relative to the other, whichever the movement is along the positive x direction. The velocity Vx decreases in successive layers away from the moving plane. This is the plane which is moving. As we go successively in layer towards the stationary phase, what happens? There is a decrease in the velocity component, the z component or x component of the velocity along this is going to be decrease in successive layers as we move along the z direction. Okay. So, what happens if there is a decrease in this direction? That means, initially it was higher velocity, finally it is lower velocity. So, what we are looking? We are getting a gradient in velocity, the change in velocity with respect to change in the distance dz. So, this will be always negative, because initially the velocity was high and now it is low. So, what we have? We have the f is in the positive direction, velocity decreases in successive layers from moving along the z direction, and the gradient along the z direction is going to be negative. Okay. Now, what is going to be the units of force? Force, we said, is mass into acceleration, and here this force is force per unit area. This capital F is force per unit area. Force is mass into acceleration. Mass into acceleration is what? Acceleration is m per second square. So, what we have? Mass, and this is acceleration, unit for acceleration, mass per second square, divided by area, m square. And what will be the gradient? This is velocity per unit distance dz. So, we have, this is the velocity, that means meters per second per meter. This is the unit for the gradient. Therefore, the unit for viscosity, now you can find out the viscosity coefficient or viscosity, you can call it viscosity or viscosity coefficient. If you apply this, you know the expression for the force per unit area, you know what is the unit for this, you multiply into z divided by dvx, and you get the expression for the eta or the coefficient of viscosity or viscosity itself. So, it is going to be from this expression meter mass inverse second inverse, and the standard books you will see viscosity coefficients are reported in Pascal seconds. What is that? You just please brush up your the definitions. 1 Newton is what? 1 kg meter per second square. So, 1 Pascal second will be 1 kg meter inverse second inverse, right. So, according to the definition of 1 Pascal second, we have a fluid with velocity, a viscosity of 1 Pascal second. What we are defining, what is 1 Pascal second? Okay. A fluid has a viscosity of 1 Pascal second if the force of 1 Newton is required to move the plane of 1 meter at a velocity of 1 meters per second with respect to the plane surface a meter away. That means, this distance is a meter away and parallel to it. So, the force required to move the plane of 1 meter, this is the 1 meter we are talking about the plane, at a velocity of 1 meters per second with respect to the plane which is maintained at a distance 1 meter apart and is parallel. Okay. So, this is goes how we can define the viscosity. So, now let us see how we can apply whatever knowledge we have from the empirical equations. We are going to again get back to this. Let us see what we have here. The properties of related to the viscosity is actually a flux of momentum. So, we have done with our definitions or understanding of viscosity. We have done it in quite a bit detail. Now, let us look at how do we use in terms of the flux. To relate the flux of momentum and the viscosity, consider a fluid in a state of Newtonian flow. Newtonian flow means they are moving in a laminar flow. They are moving in a concentric layers. Okay? All are moving in concentric layers. So, the Newtonian flow or laminar flow, which is can be imagined as occurring as a series of layers moving one past the other, sliding over each other. Okay? The next to the layer next to the wall of the vessel, here you just have a look as how it is going to look like. If this is the wall, okay, which is fixed, okay, the layer next to the wall is supposed to be stationary. Okay. So, this is going to be stationary, and the velocity of successive layers, as you see, these are, you imagine these all moving in a layers. Okay, if you can imagine them in layers, because it is actually movement in layers. So, if you can imagine that in their movement in layers, because we are looking, the picture is not very it's actually deceptive to look. It is like it is a one dimension. So, you have to understand, visualize them, this all extending to the entire tube. So, just to indicate the size difference, we have changed the height of it, but all of them are moving continuously. All these are all representing various layers. Okay. The one which is the layer which is touching the wall of the container, since container is stationary, so the velocity of that layer which is just adjacent to the wall will be stationary, and the velocity of the successive layers are going to vary linearly with the distance z. This is the direction which we are going to move. This is the tube which we are looking into. This is the along the walls of the container, and this is the z direction which we are looking into. The successive, the velocity of successive layers varies linearly with the distance z from the wall. Molecules ceaselessly move between the layers and bring the x component of linear momentum they possess in their original layer. The molecules are continuously moving, right? So, if the molecules are continuously moving, what they bring along with them, since they are moving along the z is x direction. So, whenever they are moving in the manner which is a gaseous system, it is a random manner which is moving continuously, then what it brings when they are colliding or touching each other, what do they bring? They bring the x component of the linear momentum from what they possessed in the original layer. Okay. So, this is what, let us look at it if you can see it clearly. What this part, the x component of momentum brings low momentum from the adjacent, while the molecules coming out from this layer will bring in higher x component of momentum to this. Okay. So, this layer is going to get the velocity coming out from the low momentum x component of the low momentum layer, because these gas molecules are carrying the velocity with them, and when they come in contact, then what you have? You have the transfer of momentum, and what is the transfer which is taking place? Is the x component of the momentum which is being transferred. Okay. The viscosity of a fluid arises from the transport of linear momentum. So, now you understood when we are talking about the phenomenological equations, I am going to relate to flux, and now what I am looking into? We are looking into the viscosity of a fluid arising from a transport of linear momentum. So, here we are talking about a transport of which property? The linear momentum. The fluid undergoes laminar flow, that is Newtonian flow, and the particles bring their initial momentum when they enter a new layer. Okay. Whichever whatever they were, suppose the molecules are they are ceaselessly moving, right. So, when they are in touch, they are going to another layer, they bring in the x component of linear momentum from the previous layer they are coming from. Okay. So, now if you visualize, if they arrive, see, if they arrive, that means the molecules, they arrive to the new layer, they arrive at with a high x component of momentum, they accelerate the new layer, isn't it? Because they are getting a higher component of the momentum from the adjacent layer, from previously which wherever it was, it is origin. When it comes to a new layer, then when it arrives, it is going to whatever it carries, it is going to give to that layer. So, if it is coming from a if they arrive with a higher x component of momentum, they will obviously, that means if they are coming from this side, then they obviously will accelerate the layers which is into which they are going. If they arrive with a low z x component of momentum, then they what they do? They tend to retard the layer in which they are moving in. So, a layer is retarded by molecules arriving from slow moving layers because they have low momentum in the x direction. A layer again can be accelerated if the molecules are arriving from a rapidly moving layer, okay, because they have high momentum. So, they can transfer more, the x component of momentum will be higher, which can be transferred. So, the net retarding effect is interpreted as fluid's viscosity. Okay. Now, because the retarding effect depends on the transfer of the x component of linear momentum into the layers of interest, viscosity depends on the flux. Will depend on the flux of this x component of momentum in the z direction, right. Am I clear? The retarding effect or accelerating effect depends on the transfer of what? Transfer of x component of linear momentum from initial layer to where it was to the new layer it is entering, because they are all moving, the molecules are moving. So, the retarding effect depends on the transfer of the x component of the linear momentum into the layer of interest or which we are looking into. So, the viscosity depends on the flux of the x component in the z direction, x component of the linear momentum in the z direction. So, what we have here looking? We are looking at the x component of the linear momentum along the z direction. So, the flux of the x component of momentum will be what we are going to be looking at, that is the property which for which we have the gradient for. The flux of x component is proportional to the velocity gradient along the z. Again remember, the z is the perpendicular direction and this v's velocity which we have along the x axis is the direction of the flow. The flux of the x component of momentum is proportional to the velocity gradient, because there is no net flux, when all the layers move with the same velocity. Okay. Flux can be only generated when you have different layers have different velocity. So, the constant of proportionality which we can have, so the flux of x component of momentum is going to be proportional to the velocity of the velocity along the z direction, x direction, with the distance dz, which is perpendicular to the direction of flow, that is Vx. Okay. The constant of proportionality can be put in, and this is known as the coefficient of viscosity or viscosity. And what is the unit? We have done this in the previous class. Q is equal to kg meter inverse centimeter inverse, and some books you will, even today when you are reporting, viscosity not only is represented in terms of Pascal seconds, it is even more common to find viscosity coefficient or viscosity reported in terms of poise. What is 1 poise? 1 poise is 0.1 or 10 to the minus 1 kg meter inverse second inverse. So, if you are looking into the meter inverse in MKS system, then you have this, and usually it is taken as standard books will give you in Pascal seconds. Okay. So, to calculate transport coefficients, we need to consider how the Maxwell's distribution is disturbed by the gradient in concentration, temperature or velocity. Okay. So, if you want to find out what these coefficients are, diffusion coefficient, thermal coefficient or viscosity coefficient, using the hard sphere model, what we need to know how the Maxwell's distribution of the molecules in terms of speed is going to be disturbed by the gradient in concentration, temperature and velocity. This calculation is not going to be easy. So, this is not going to be part of the syllabus, but based on the kinetic model, we can lead to some expressions for the diffusion parameters. These are the diffusional parameters which we are talking. These are the diffusion coefficient, thermal coefficient and thermal conductivity or thermal coefficient, and viscosity or viscosity coefficient. And the diffusion parameters of such gases is summarized in this table. So, we leave this at this. We begin the next class from this particular slide. How see diffusion, these are the properties which we are looking into. What is the quantity which is getting transported? When you have a diffusion process, these are transport properties, processes. This is diffusion process, you have matter transported, and what is the from kinetic theory, what do we get? We are going to discuss starting from this slide in the next class. Thank you.